Hello, in this video we're going to learn a couple of new terms for acids and bases, and that's conjugate acid and conjugate base. So we already looked at the reaction between ammonia, which is a base, and water, which is an acid, and you can see that down below. So we've got water reacting with ammonia to produce the hydroxide ion and the ammonium ion. So the terms conjugate base and conjugate acid are for the products specifically. So once an acid has given up a proton, so a hydrogen ion, those are the same thing. So remember, hydrogen has only one electron. So if it gives that electron up to become positively charged, all that's left in hydrogen is a proton. So sometimes we use those terms interchangeably. So once an acid has given up a hydrogen ion or a proton, the part that remains is called the acid's conjugate base. So down below, water was acting as an acid and it gave up a hydrogen ion to ammonia. So what was left at the end is the conjugate base of the acid. And the reason that we call it a base is the hydroxide ion, or what's left over from the acid, that can act as a base if we go in the reverse direction. So similarly, the part of the base that remains after it accepts a proton, so a hydrogen ion, is called the base's conjugate acid. So ammonia was acting as our base, and once it gained a hydrogen ion, it became an acid, the ammonium ion. Now, notice that this has a double arrow in the middle, so that means this reaction can go backwards and forwards. So the products, the conjugate base and the conjugate acid, they could react with each other and reform water and ammonia, the reactants. So again, these terms, conjugate acid and conjugate base, are specifically for the products. Now, once we know which one is which, we can refer to conjugate acid-base pairs. So water and its conjugate base are a pair, and ammonia and its conjugate acid are a pair. Now, water, we lost a hydrogen ion to become OH minus, and then ammonia gained a hydrogen ion to become the ammonium ion, NH4 plus. All right, and I'm using a PDF copy today because my PowerPoint slides were not showing the equations. So if you're having the same issue, feel free to use the PDF copy of the lecture slides. All right, so let's practice. Let's identify the conjugate acid-base pairs in this equilibrium reaction. So in this reaction, we have two reactants. We have something called acetic acid, which is in vinegar, and that's what gives vinegar its smell, whether you like the smell or not. And then water, of course, is just H2O. And then in the products, we have the hydronium ion and acetate. All right, so looking at our name, acetic acid, we can probably guess that that is the acid, right? Now, that means that water has to act as a base in order to form the products. So looking at the products, see if you can figure out which one is the conjugate acid and which one is the conjugate base. So pause the video, try that on your own first, and then we'll go over it together. Okay, so remember, acids are going to give away a hydrogen ion, or a proton, we could call it. So it looks like our acid is going to give up its hydrogen on the end and form the acetate ion. All right, and since we started with an acid, what would we call that product, the acetate product? Would that be a conjugate acid or a conjugate base? A conjugate base. So it's always going to be the opposite, right? So our acid is going to form a base in the products, and then our base, in this case water, is going to form an acid, the conjugate acid. Okay, so those are the acid-base pairs, or the conjugate acid-base pairs. Acetic acid and acetate are one pair, and then water and the hydronium ion are another pair. All right, so now that we know those terms, let's talk a little bit about strong acids and bases. So there are a small number of acids that turn into ions completely in water. So everything turns into ions. For example, when hydrochloric acid, HCl, dissolves in water, every single molecule of HCl is going to separate into a hydrogen ion and a chloride ion. Now, sometimes we write this a little bit differently. Sometimes we show the reaction with water. Oops, let me rewrite that. And we show that HCl gives up a hydrogen to water and forms the hydronium ion. And then what's left over from HCl is Cl minus. So sometimes H3O plus, the hydronium ion, is used in place of the hydrogen ion. It just depends on how you write the reaction. Are you actually showing the reaction with water, or are you just showing HCl breaking apart? But both are true and both are accurate. Now, similarly, a strong base is a compound that essentially 100% ionizes in solution. So it completely breaks apart, and we don't have any leftover reactant. So really strong acids that completely break apart in solution are HCl, so we already talked about that, hydrochloric acid, and then hydrobromic acid, hydroiodic acid. So notice these all have halogens in them. Although we're missing fluorine. Hydrofluoric acid, HF, is actually a weak acid, so it's not included in this list. Now below that we have a few more. We have nitric acid, HNO3, sulfuric acid, H2SO4, and chlorate acid, HClO4. So those are all of the strong acids. So it's just a good idea to have some of those in your back pocket. Well, not literally, you don't want acids in your back pocket. But just remember the strong acids, right? Now, strong bases are typically going to contain a hydroxide ion. So lithium hydroxide, sodium hydroxide, etc. So those are all really strong bases. Now, any other acid or base that's not on this list is typically going to be considered a weak acid or weak base. So if an acid is not a strong acid, it's likely a weak acid. And that means that it doesn't completely ionize in solution. So it doesn't, not every molecule is going to break apart in solution. And same for weak bases. Not every molecule is going to break apart in solution. So for example, acetic acid, which we just saw earlier, is a weak acid. So it's going to produce some product, so some conjugate base, but some of it just stays the same. It stays acetic acid. So depending on the concentration of the acetic acid, only about 1 to 5% of the acetic acid molecules will break apart or ionize in solution. So what we actually see is an equilibrium reaction. So does the chemical reaction describing the ionization of a weak acid or base stop when the acid or base is done breaking apart or ionizing? No, it actually goes back and forth. So in this case, reactants would be favored because we just said that only about 1 to 5% of those acetic acid molecules will break apart in water. So reactants are favored and products are not favored. But this reaction can go back and forth and eventually it will reach equilibrium. All right, so again, this is going to be a dynamic equilibrium. So even if we reach equilibrium, that doesn't mean the reaction has stopped, right? It's still going back and forth. It's just that the concentrations of the reactants and products are staying the same. So that actually brings us to the acid ionization constant, Ka. So this is going to tell us whether reactants or products are favored at equilibrium. So this is going to be really, really similar to our equilibrium constant that we learned about in chapter 9. But this one is just very specific for acids. All right, so let's look at a generic equation for a weak acid, or reaction, I should say. So we're starting with our acid, HA, and in water, it's going to break apart into the hydrogen ion and a conjugate base. So remember, when we talked about the equilibrium constant, we wrote the concentration of the products over the concentration of the reactants. And we're going to do the exact same thing for our acid. So this constant, which we'll label Ka for acid, is equal to the concentration of our products, H plus and A minus, over the concentration of the reactant, HA. So this is just going to represent the fraction of the original acid that has been ionized in solution. So again, this will tell us if products are favored or if reactants are favored. And that can tell us how strong the acid is. Because remember, an acid like HCl, we said that completely ionizes. So everything turns into ions. So that would mean we only have products in solution. So we should see a pretty high number for the Ka of HCl. But if we have a weak acid like acetic acid, then we have mostly reactants and the number should be pretty small. So let's look at some Ka values for different acids. So again, the numerical value of Ka reflects the strength of the acid. So if an acid has a higher Ka value, they're going to be stronger. So let's look at sulfuric acid. We said sulfuric acid was a really strong acid earlier. So it should completely ionize in solution. And in fact, its Ka value is really, really large. Now that's for the loss of one of its hydrogens. But our conjugate base could lose another hydrogen, right? And that has a slightly lower number if it loses that second hydrogen. All right, now let's look at acetic acid by comparison. So we saw the reaction for that earlier. This has a pretty low value, around 10 to the negative 5. So that means it's a pretty weak acid. And notice that these numbers are getting smaller and smaller as we go down the list. So that means that these acids are getting weaker and weaker. So the strongest acids are at the top, the weakest acids are at the bottom. All right, so we can actually do the same thing for bases. We could calculate a Kb value instead of a Ka value. Oh, I have a typo on here. So the ionization for a weak base, which we'll call ROH, not HA, can be written as the following. So ROH can separate into its conjugate acid and a base, OH minus. Now, again, we can write this as an expression for Kb, where again we put product concentrations on the top and reactant concentrations on the bottom. So this will be our equilibrium expression for a base. And again, the base ionization represents the fraction of the original base that has ionized in solution. So if we have a really strong base like NaOH, that's going to completely ionize in solution to give us sodium ions and hydroxide ions. And because everything turns into ions, we would only have products at the end. And so our Kb value would be really, really large. So let's look at some examples. So again, the numerical value of Kb is a reflection of the strength of the base. So ammonia is actually another fairly strong base, although it's not technically a super strong base. It's kind of in the middle. But that has a Kb value on the order of 10 to the negative 5th, so somewhat similar to acetic acid. And notice that our values are getting smaller as we go down, so the same thing here. We have stronger bases on the top and weaker bases on the bottom. All right, so I think we're going to stop there for this video. And then in the next video, we're going to talk about a very special case for acids and bases, water. So water is interesting because it can act as an acid and a base. So we'll dive into that next.